Section 4b in your textbook deals with the converse of Pythagoras' theorem. So you'll remember from section 4a that Pythagoras' theorem says if we have some right angle triangle, then we know that the relationship of the sides will be such that a squared, one of the legs of the triangle, plus b squared, the other leg of the triangle, are going to be equal to the longest side, or the hypotenuse, squared. Pythagoras' theorem has to assume that this is a right angle triangle, this part here. Yeah? Only right angle triangles have this relationship. If we just take any old triangle, something like this, then this relationship doesn't exist. First of all, you have to ask yourself, where's the hypotenuse? Which is the longest side? Maybe this one? But unless this angle here is a right angle, Pythagoras' theorem won't hold. So the converse of Pythagoras' theorem says that you can use this to prove that something is a right angle. If I have some triangle, let's just draw it like this, and this angle here, well, that kind of looks like it might be a right angle triangle, but I don't know for sure. If I measure the sides and get something like 5 here and 12 here and 13 here, I've measured them all, then I can check to see if this is a right angle by seeing if it fits Pythagoras' theorem. And that's what we mean by converse. Converse is a type of inverse, or a type of opposite. Means instead of starting with the right angle triangle and using Pythagoras' theorem, we're going to start with Pythagoras' theorem and use it to prove the right angle. Okay, so we're looking at this angle. We want to see if that's the right angle. Why does it have to be that angle and not this one? Well, I look at which side is the longest. I've got 5, 12, and 13. These are pretty similar, but 13 is the biggest one. So 13 must be the hypotenuse. And the hypotenuse is always across from the 90-degree angle. So this is the angle that we have to consider. This will not be a right angle because otherwise 12 would have to be the longest side. Okay, so 13 is the hypotenuse, 5 and 12 are the legs. So I'll set up Pythagoras' theorem. If it's a right angle, then this should be true. Equals the hypotenuse squared. So we have to know our squares, or if you don't know them, use a calculator. 5 squared you should all know, and if you don't, it's time to memorize the squares up to 100. Okay, so that's 25, and 12 squared is 144. You might remember that from your 12 times tables. 13 squared, a few of you may know, that's 169. So the question is, are these equal to each other? Maybe I should have put a question mark by the equal sign here until I know that they're equal to each other. So 25 plus 144, well, the 5 plus 4 is equal to 9, so that's looking good so far. 20 plus 40 is equal to 6, and then we have 100. So is 169 equal to 169? Well, yes, it is. So this is a right angle triangle. And then I can write it in and say this is the right angle. And I can also erase my question marks because those are equal to each other. So that's what you're doing in this section, is you're using Pythagoras' theorem to check whether angles are right angles or not. And remember, you always use the longest side as the hypotenuse. So when you're setting up your equations, then put the longest side by itself and the other two legs squared on the other side. Let's do one more example. Let's say I have a triangle and I measure its sides and I come up with 6 centimeters on one side and 8 centimeters on another side. And I don't know why I would measure this, but for our math textbook's purposes, we'll assume I measured the square root of 21 centimeters on the other side. Probably I didn't measure it, probably it was given to me. So I have this triangle. I know that these are the 3 sides. I'd like to prove whether there is a right angle triangle in it. First thing I need to ask is, which is the longest side? So these two are easy to compare. 8 centimeters is longer, but what about this one? Of course, you could plug it into your calculator, but there's a faster way as well. If you think about square roots, then we know that 16 square rooted is going to equal 4, and 25 square rooted is going to equal 5. So anything between 16 and 25 is going to have a square root between 4 and 5. So I know this is 4 point something. That means it's actually the smallest side, and this is my biggest one. So that's the hypotenuse. I'm going to set up 8 squared. The hypotenuse must be equal to the 2 legs squared. Notice it doesn't matter what order I do Pythagoras' theorem. It holds if I do c squared equals a squared plus b squared as well. It's getting a bit in the way. So let's square those sides. Okay, 8 squared is 64. 6 squared is 36. And square root of 21 squared, squared undoes the square root, is just 21. So I add those two together. The ones make 7. Well, that's not looking good. And the 3 plus 30 plus 20 gives me 57. So 64 is not equal to 57. That means this is not equal to each other, and that's not equal to each other either. So this is not a right angle. And since I don't have an angle to label, I will call it a right triangle. This is not a right triangle, meaning the triangle doesn't have a right angle. That's enough to get you through 4b.1. That's what you're practicing basically, is checking to see if there's right angles in the triangles. In section 4b.2, we're introduced to Pythagorean triples. And those are basically, they're called triples because it's always comes as a set of 3 numbers. And we always put them in braces. I'll just use some letters for now before we actually fill it with numbers. So this is how we write them. Pythagorean triples are 3 numbers that satisfy the Pythagoras' theorem. So if I would take this number squared plus this number squared, I should get this number squared. So over here with 5, 12, and 13, we actually have an example of a Pythagorean triple. So if I'd write 5, 12, and 13, and we usually order it from smallest number to biggest number so the hypotenuse is clear, 5, 12, and 13 is a Pythagorean triple. Another really common one is 3, 4, 5. 3, 4, 5 also satisfies the Pythagorean theorem. If I take 3 squared plus 4 squared, I get 9 plus 16, and 9 plus 16 equals 25, which is the same as 5 squared. So that's another Pythagorean triple. And in section 4b.2, you are going to be examining Pythagorean triples and checking to see if the sets of 3 numbers are Pythagorean triples or not. What does this have to do with the rest of life? Yeah, what are Pythagorean triples all about? Well, Pythagorean triples probably don't have a really obvious application into sciences or into economics or something like that, but mathematicians have been playing with them for a long, long time. And yeah, why? I guess because it's kind of neat, isn't it, that 3 squared plus 4 squared equals 5 squared? Because 2 squared plus 3 squared doesn't equal 4 squared. That doesn't work. And 4 squared plus 5 squared doesn't equal 6 squared. And there's lots of consecutive numbers that don't work like this pattern. And then suddenly 5 squared plus 12 squared does equal 13 squared. So some mathematicians started thinking, this is kind of interesting. I wonder how many of these there are. And so there are actually pages and pages of work done. Let's take a look at one of them. If I just click onto here for a second. Get rid of that. And move that. Okay, this is from a website called Wolfram Math World, who is a nice one to look up if you're looking for various math things, although it's sometimes a little bit complicated. But you see that when people started graphing certain relationships with Pythagorean triples, that they got some pretty interesting patterns. And you might not believe it, but the rest of this site all deals with the math behind Pythagorean triples. And yeah, looks pretty complicated to me. So there's something there, there's some patterns there. And in fact, the Pythagorean triples eventually leads to something called Fermat's last theorem, or Fermat's last theorem. And why was it called his last theorem? Well, Fermat was a very, very, very smart man who lived around the 1600s. And in fact, he came up with all kinds of math theorems that people around him didn't understand. And the problem was he was so smart, he just sometimes didn't write down how he got it, or maybe his works were lost, or we don't exactly know why. We don't have his proofs, but he just, said certain things and then assumed they were true, and no one else knew why, and no one else could prove it. And Fermat's last theorem was the very last one to be proved. So it took mathematicians sometimes 200 or 300 years to figure out what he had done. And he came up with a theorem in 1637, and it took people till 1994 to prove it. I still remember growing up in school and people saying Fermat's last theorem has not been proved yet. And shortly after I graduated from high school, it was proved. And it was a big news item at the time for mathematicians for sure, but it also made it into popular news. And his last theorem said, okay, well, if Pythagorean theorem is true, that you can square any number, what if we cube two numbers? And now we're not talking about triangles anymore, because we can't draw something we can draw something that's cubed in 3 dimensions, but he also did it for 4 dimensions and 5 dimensions and 6 dimensions and so on. He said, is there going to be any n bigger than 2 that's going to make this relationship true? And his theorem was to say, no, there isn't. Squared numbers are the only numbers that have this relationship. And he said he proved it. He came up with some mathematical proof that says, even if I go up to, 3,546, a to the 3,546 plus b to the 3,546 equals c to the 3,546, you'll never ever find another n, another power that works like this. Yeah, and it took them till 1994 to prove it. And really, honestly, I don't understand the proof. So maybe some of you will someday. Okay, good luck with section 4B.